Let's derive the rotational analogue of Newton's second law. And this equation applies for a rigid body that's rotating about a fixed axis, or where the rigid body is free and rotating about its center of mass. So we can write Newton's second law for particle I, and then taking a cross product with the radial vector gives the torque. And we can write the acceleration in terms of the angular acceleration. With the angular acceleration is in the direction of the torque, and it's a vector that points out of the screen, which we can also represent as follows. And because the mass is a scalar, we also took it out of the cross product. And I encourage you to evaluate these cross products, and you'll end up with the following vector. Because crossing alpha with the radial vector gives a perpendicular vector to both vectors, and then crossing with RPI again gives a vector that points out of the plane. So now we can write this as a scalar and take the sum over all the particles in the rigid body. And if you take the limit as n approaches infinity from both sides, you'll end up with the net torque about P is equal to the moment of inertia about P by the angular acceleration. And the angular acceleration is uniform on the entire rigid body. We can draw rigid body diagrams which help us to apply the rotational analogue of Newton's second law by identifying the position of each force on the rigid body. So for this first example on rolling motion, we have the force of weight, the normal force, and the force of static friction where there's no slip. And for this rotating rigid bar, we have an oblique force, so we must have a horizontal and vertical reaction to prevent the bar from translating at the hinge, and we have a force of weight through the center of mass. And for this cable pulley system, where we consider the geometry of the pulley, we can split this up into 3 bodies and then draw the forces acting on each body. And here we have the self-weight of the pulley, and also a reaction at the hinge to prevent that pulley from translating at the hinge. A bar is restrained at its base and subjected to a force. Write the linear accelerations at points A and C in terms of the following variables. What we do is draw the forces acting on this rigid body, which has a mass m. So there must be reaction forces preventing the bar from translating at the hinge. So if we take a sum of torques about the hinge, only the horizontal component of this force contributes a torque. And that's equal to the moment of inertia of the bar about its endpoint by the angular acceleration. And now we can solve for alpha. And therefore, to find the linear acceleration at A and C, we can use the following relationships. A rigid bar is sitting freely on a horizontal frictionless tabletop and subjected to a force as shown. Write the linear accelerations at the following points in terms of the force and the mass of the bar. So this problem tells us that the force of weight and the normal force act in and out of the plane. So that means the bar is in equilibrium in the z direction. Now applying Newton's second law in the horizontal direction, we have the force is equal to the mass by the acceleration of the center of mass, and that gives us the acceleration of the center of mass due to translation. And now we apply the rotational analogue of Newton's second law where the torque is taken about the center of mass, where the bar is free to rotate. So the torque, which is the force by the moment arm, is equal to the moment of inertia of the bar about the axes passing through the center of mass by the angular acceleration. And that gives us the angular acceleration of the bar. And from that we can calculate the acceleration at each point by superimposing the translational and rotational components. And the acceleration at C is the acceleration of the center of mass, which is purely translational. So what this superposition looks like is translation plus the rotational component is equal to the acceleration of the bar. We can apply Newton's second law for translational and rotational motion to a dynamic system that's translating and rotating. We derive the following kinematic relationship between the translational velocity of the center of mass and the angular velocity of the disk. And the same thing for the acceleration of the center of mass, which is related to the angular acceleration. And under the no-slip condition, we have a force of static friction, because in rolling motion without slip, the rotational and translational motion cancel each other out. And we have a force of weight acting through the center of mass, and also a normal force acting in a perpendicular direction to the plane. And a disk has a radius r. Now applying Newton's second law for translational motion in the direction parallel to the plane, we have the force of weight sine theta minus a static friction force is equal to the mass by the acceleration of the center of mass. And applying Newton's law for rotational motion by taking the torques about the center of mass, well, we eliminate the torques produced by all the forces except the static friction force. And the moment of inertia of the disk about the center of mass is as follows. And now using this relationship, we can rewrite alpha, and then dividing through by r, we cancel out these terms. And then adding these equations together, from which we obtain an expression for the acceleration of the center of mass. Two blocks are attached to a fixed cable pulley system, and the masses of the blocks and the pulley are given, as well as the radius of the pulley. And we're asked to calculate the forces in the cable and angular acceleration of the pulley, assuming no slip between the cable and pulley. So if we isolate the bodies and draw the forces acting on each body, so we have the force of weight on each mass and the tension forces at those 2 points of the cut. Which are equal and opposite on each body due to Newton's third law. And because the blue block is heavier, we expect the accelerations as follows. Now applying Newton's second law on each block, and note that we'd also have a force of weight on the pulley and a reaction force, because the hinge prevents the pulley from translating but allows it to rotate. But when we apply the rotational analog of Newton's second law and take the torque about the center of mass of the pulley disc, we eliminate the torques produced by these forces, where the moment of inertia of the pulley disc is as follows. And note that because there's no slip between the cable and pulley, the accelerations at these points on the pulley are the same as the accelerations of the blocks. So therefore we can relate them to the angular accelerations as follows. And now you can divide through by r, add all these equations together to eliminate the tension forces, and then substitute for the accelerations and solve for the angular acceleration. And from that you'll be able to solve for the forces in the cable using these equations. And post your answer in the comments. A cylinder with a mass m and radius r unrolls vertically from 3 strings tied at one end. Find the acceleration of the center of mass. Well, drawing a free body, we have the tension forces in the cables and the force of weight of the cylinder. And if we observe these forces in the plane of the cross section of the cylinder, they would look something like this. So now we can apply Newton's second law for translation to get the acceleration of the center of mass, and we can apply the rotational analog of Newton's second law to obtain an expression for the angular acceleration. Then dividing through by r and adding these equations together, and assuming the no-slip condition, the acceleration of the center of mass is related to the angular acceleration as follows. So therefore, substituting for alpha, you'll get the acceleration of the center of mass as follows. Recall Newton's second law with the rotation about a fixed axis and the kinematic relationships for angular velocity and angular acceleration. Well, we can eliminate dt from these relationships to obtain the following expression, and then substituting for the angular acceleration, and separating the variables. And now we can integrate both sides of this equation, where the moment of inertia is constant. So this is the rotational work on the left-hand side of the equation, which is equal to the change in rotational kinetic energy. Previously we derived an expression relating the rotational work due to the rotational kinetic energy of a rigid body rotating about a fixed axis. Well, in this case we consider a rigid body that's free to translate and rotate in a plane. So what we have is the following expression for the rotational work due to the net torque about the center of mass. And that's equal to the change in rotational kinetic energy when we take the moment of inertia about the center of mass. And similarly, we had an expression for the translational work. So that would be due to the net force acting on the body. And that's equal to the change in translational kinetic energy. So we have the mass, or the velocity of the center of mass of the rigid body, where the squared magnitude is the same as the dot product between the velocity vector and itself. So in this case, we have a work kinetic energy relationship for rotation and translation, which is applicable to cases such as rolling motion of a rigid body. A disc has a mass of 10 kilos and a radius of 3 centimeters, and it's initially at rest and subjected to the following torque, which is a function of the angle theta. And we're asked to find the velocity of point P on the rim if it traverses 12 radians. Well, the work done by the torque is the integral from the initial to the final angle of the torque with respect to theta. and that's equal to the change in kinetic energy of the disk, which is a half by the moment of inertia about the center of mass by the change in the square of angular velocity. And recall that the velocity is related to the angular velocity by the radial distance from the point where the torque is applied by the magnitude of the angular velocity. Well, if we evaluate the integral on the left hand side, and on the right hand side, the moment of inertia of the disk about the center of mass is mr squared on 2, where the disk is initially at rest, so omega naught is 0. And if we take our reference angle of theta naught is equal to 0, then this is 0, and we obtain the following expression for the angular velocity. So you can substitute the given values to find the angular velocity, then multiply it by r to get the velocity at point P. A bar is initially at rest and hinged at point P, and a variable force is applied at the base, where a is a constant, and we're asked to write an expression for the angular velocity as a function of theta, assuming the force remains perpendicular to the bar. So recall the rotational work kinetic energy theorem. So given the bar is initially at rest, and the moment of inertia of the bar about its endpoint is as follows, where m is the mass of the bar, and we have a force of weight acting through the bar at the center of mass. So at some angular position of the bar, theta, it looks something like this. So therefore we can rewrite the net torque about the pivot as follows. So the torque due to the force acting at the end of the bar is as follows, where the moment arm is L, and the torque due to the force of weight is mgl on 2 sine theta. And now you can evaluate the integral, solve for the angular velocity, and post your answer in the comments. We can apply the conservation of energy to some types of rigid body motion, such as rolling motion without slip, where the following forces are acting on the body, as we've seen. And because we have a static friction force, so there's no energy dissipated because there's no slip between the surfaces, or the instantaneous velocity of the contact point is 0, then the total mechanical energy is conserved. So if we have the initial and final position of the body, then the total initial energy, consisting of kinetic and potential energy terms, is equal to the total final energy. And in rolling motion without slip, the total kinetic energy consists of a translational term and a rotational term, where you can take advantage of the following relationship between the velocity at the center of mass and the angular velocity of the body, as we've derived for rolling without slip. Now the potential energy, on the other hand, depends on the mass of the body, the gravitational acceleration, which is uniform on the body, and the height above some datum. So for example, if we choose our datum point over here, then we take the height as the vertical distance from this datum point to the center of mass of the body. A disk with a mass of 2 kilos and radius of 2 centimeters starts from rest and rolls down an inclined plane without slipping. Determine the velocity if the body travels 5 meters as shown. So let's apply the conservation of mechanical energy, where the total initial energy is equal to the final total energy. So given the body starts from rest, this is 0. And if we take the final center of mass as our reference point, then the initial potential energy can be written as follows, where h is the initial height of the center of mass above this point. So therefore the final potential energy is 0, because we took the reference point at the final center of mass. So the final kinetic energy consists of translational and rotational terms. So for rolling motion without slip, we had the following relationship. And knowing the moment of inertia of the disk about its center of mass, and substituting for the velocity of the center of mass in this term, then we can do some cancellations and we get the following expression, which we can solve for the velocity of the center of mass. And you can determine an expression for h using trigonometry. Two blocks are attached to a fixed pulley using a massless cable, and block 1 is released from rest. Find the speed of the block at the instant before it hits the ground, assuming no slip between the cable and pulley. So applying a conservation of energy to the entire system, mass 1 has an initial potential energy, and that's equal to the final energy of the system before the blue block hits the ground. So for that to happen, mass 2 will move up a height h. And we add the kinetic energy of both masses, which are travelling at some speed v. And then plus the rotational kinetic energy of the pulley, which is going to have the same speed at the rim due to the no slip condition. So therefore v is related to omega using this expression. And note that we didn't include the potential energy of the pulley because it's fixed. So therefore the potential energy terms will cancel on both sides of the equation. And now you can do some cancellations and solve for the speed of the block before it hits the ground.